Explain with two examples each of the following. Coordination entity. Now there are 6 or 7 terms. I am supposed to explain you each term and give you a couple of examples. What is coordination entity? Coordination entity is an entity or a group of atoms in which a central metal atom is attached to a set of ligands. What? The entity in which a central metal atom is attached to a set of ligands or lone pair donors is called a coordination entity. For example, you could have Cu NH3 whole 4 2 plus. Is this a coordination entity? Yes. You could have NiCO4. Is it a coordination entity? Yes. Another different one. They are not same. They are different molecules. Or you could have FeCN6 4 minus. Is this a coordination entity? Indeed. The coordination entity, sometimes it is also called by another name, coordination sphere, may have positive, negative or zero charge. And it consists of a metal atom at least, which is attached to a set of lone pair donors or Lewis bases like ammonia or carbon monoxide or cyanide. That, my dear, is a coordination entity. Instead of 2, I have given you three examples. You can take any two you like. This is done. Now let's take the second one, ligand. What are ligands? Ligands are lone pair donors or Lewis bases. What are ligands? Ligands are Lewis bases or lone pair donors. Lewis bases which are attached to a central metal atom through coordinate covalent bonds. So, if I have nickel which has formed coordinate bonds with carbon monoxide, say for example, this is an example, a very classic example of a ligand. In this case, nickel is attached to 4 ligands, as you can see, 1, 2, 3 and 4. Nickel is the central metal atom and each carbon monoxide functions as what is called actually a ligand. So, is carbon monoxide a ligand? Yes, very much so. Similarly, ammonia could be a ligand. Similarly, cyanide ions could be a ligand. Any lone pair for that matter, any lone pair donor. And who's a lone pair donor? Actually, if you have a lone pair, you can always donate it. So, any entity with a lone pair, in potential, yes, it can function as a ligand. Second point. Now, we are done with these. What is coordination number? That also is very interesting. What is coordination number? The number of lone pairs or the number of electron pairs which are donated, or the number of ligands. Not really. A more accurate version would be this. The number of ligand atoms directly attached to a single central metal atom is called the coordination number of that metal atom. What? Let me say it again. The number of, like this is 1, 2, 3 and 4. The number of ligand atoms, directly attached to one central metal atom is called coordination number of that metal atom. Please note, coordination number is a number which is attached with a central metal atom. So, depending upon the number of ligand atoms which are directly connected to metal atom, you decide the coordination number. There are many approximate or wrong definitions also of coordination number. A very stupid definition is the number of ligands attached to metal atom is coordination number. Obviously not. Why? Just look at this. I have a lovely oxalate ion, and the loveliness of oxalate ion is that it possibly can donate not 1 but 2 lone pairs to nickel. Say for example like this. Now if this is the only thing, what is the coordination number of nickel? It has only one ligand attached. But how many ligand atoms? 2 ligand atoms are directly attached. So the coordination number because of this attachment will be counted as 2, not 1. Although there is only one ligand, but there are 2 atoms directly connected. So coordination number will be 2 because of this. That is why I said the number of ligand atoms directly attached to metal atom, that is the coordination number, and that is something which you need to remember or not forget. Very important point of distinction, coordination number. Then we have something which is called as coordination polyhedron. Wow, what is that? Actually, the geometry around this central metal atom, that would be termed as coordination polyhedron. What does that mean? If you take a coordination sphere and you talk about the geometry around that coordination sphere or the polyhedron which would be drawn in case all the ligands are connected and they are assumed at the corners of a polyhedron, that is a coordination polyhedron. Metal atom must be the centroid and the ligand atoms must be the corners of the polyhedron. Like, say for example, if you have linear geometry, that's pretty simple. But in case you have tetrahedral geometry, for example, NiCO4 is tetrahedral. So coordination polyhedron around nickel atom in NiCO4 is tetrahedral. And again I repeat, this coordination polyhedron is an imaginary polyhedron which will be formed by joining all the ligands attached to a single given metal atom. And that metal atom should be present at the centroid of that polyhedron. If I have to give you a couple of examples, yes, I'll give you. Say for example, if you have FeCN6 4 minus, lovely, yes. This has octahedral polyhedron because if you if you connect all the 6 cyanide ions, they actually are at the corners of an octahedron. On the other hand, if you take something which is simpler, like let's say take Zn CN4 2 minus. This is tetrahedral. Why? Because if cyanide ions are connected to each other, you would find that they are at the corners of a regular tetrahedron. Zinc ion being at the centroid of that tetrahedron. So these are, my dears, coordination polyhedra. Then they have asked homoleptic and heteroleptic. If all the ligands are identical, then the coordination compound is called homoleptic. Like if I have 6 ligands, all of them are cyanide, this is homoleptic. If I have 4 ligands and all of them are cyanide, it is again homoleptic. So 2 examples of homoleptic are also these. They are homoleptic complexes. What is heteroleptic? If more than 1 ligands are present within the same coordination compound, then that coordination compound, my dear, would be termed as a heteroleptic compound. Like, you could just write down anything practically and that would work out. Like, say if I have rhodium, and anything, something fancy I'm taking. Now you take PPH3, whole thrice, Cl, something of that kind. Now, if you have this, then there are 2 ligands, triphenylphosphine and chloride. How is this? This is an example of a heteroleptic complex. If you want to keep it simple, well, Fe, NO, CN5, NO2 minus. This is sodium, this is nitroprusside ion, for example. It has 2 different ligands, NO and CN. So cyanide and nitrosodium cation actually. Now, together they make a heteroleptic complex. Why? Because all the ligands are not identical. That's why. These are the definitions with 2 examples each.